In this lecture, we are going to discuss chemical reactions in terms of the energy that they possess, or the amount of energy they absorb or that they release. We'll talk about the rate of a reaction, and we'll talk about reversible reactions and how they reach what we call equilibrium. So let's just start with a quick review of energy and matter. So again, this is going back to the beginning of the quarter. We talked about how to study matter. We also need to study energy. And we've spent a fair amount of time now talking about matter. We've described atoms and we've described nuclear decay equations. And we've also talked about molecules. We've talked about how atoms can form ionic and covalent bonds to form compounds and molecules. And in our last series of lectures, we discussed how those molecules or inorganic compounds can react with one another to form new molecules or compounds. So now we're gonna talk about those chemical reactions a bit more, and we're gonna look at the energy that's involved in chemical transformations. So within this category of energy, we have two types. We have potential energy, and this is really the energy that's stored in chemical bonds. And so that means that when this bond forms, it releases energy, and it requires energy to break that bond. And for this example, this is water. That's about 500 kilojoules for every mole of water that you have. The other type of energy that molecules possess is kinetic energy, and that's really how it moves through space, how it rotates, how it wiggles, how it zips around the room if it's a gas. So let's focus a bit more on energy and do a little bit of basic definitions and then talk about units. The total energy of any system is going to be equal to the sum of its potential energy and its kinetic energy. So again, that potential energy is the energy in the bonds of our molecules, and the kinetic energy is how those molecules are moving around. And energy is really the capacity to do work. If you've taken a physics class, you've spent more time on this. But the capacity to do work is just really applying a force through distance, kind of like someone moving a really heavy box. That takes some work, right? So if we have our potential energy as stored energy and our kinetic energy is motion, and we know that the total will be the total energy. We can also look at the conservation of energy right here. The conservation of energy, or the law of conservation of energy, states that the total energy of the system, so that's the potential plus the kinetic energy, won't change. And that really just means you can't create energy from nothing, and you can't destroy energy. So as chemists, we're going to look at how energy flows through systems, and it's really going to look at how does energy flow between potential and kinetic energy, or from one part of a system to another. Let's look at some examples of what we mean by kinetic and potential energy. So kinetic energy is that energy of motion we've talked about. And some examples of this would be a car moving down a roller coaster. So at the top of a roller coaster, you would have zero kinetic energy. And because there's that terrifying pause at the top of the roller coaster. And then as it starts going down quickly, your kinetic energy increases. And by the time you're at the bottom of the hill, you have all this kinetic energy and no more potential energy. Now, potential energy, if it's that stored energy, is going to be when you're at that top of the roller coaster, that pause, that's when you have all of your potential energy. And then as you go down the roller coaster, that potential energy is decreasing. And so the potential energy is being converted into kinetic energy. Until at the bottom of the roller coaster, we don't have any more potential energy, just kinetic, and you're going really fast. Other examples of kinetic and potential energy would be if we think about a spring. So when the spring is compressed, when it's coiled up really, really tightly, it has a lot of potential energy. And the second it's released and it's moving out, that's when you have kinetic energy. Now, within chemical bonds, the chemical bonds in gasoline or food or coal, those have potential energy. That's our stored chemical energy. And then when they're moving, they are exhibiting kinetic energy. We've talked about combustion reactions. And so if we had octane and we combust it, so this is gasoline, we would form carbon dioxide and water, which are more stable elements. And we would actually be breaking all of these carbon-carbon bonds and carbon-hydrogen bonds and forming new carbon-oxygen bonds and carbon-hydrogen bonds. And the process of this all together is going to actually release energy as well. And this is what we're going to talk about in this chapter too. And so this energy can be motion, and we also experience kinetic energy as heat, which I hope is my next slide. It is. So heat is a specific type of energy that we call thermal energy. And it's a kinetic energy. It's kinetic energy. It's like a subset of kinetic energy. So it's associated with the movement of particles. And the faster particles move, the greater heat or thermal energy they have. So as if temperature and heat are the same, as temperature increases, the kinetic energy of those particles is increasing. And so if we think about an ice cube, in the solid state, water molecules are not moving translationally. And that means they're not moving past each other. They're vibrating and twisting around in place. But as heat is applied to the ice, as you input heat to that ice, it melts. And those water molecules start moving faster and faster. So when they were in a nice rigid state in the solid state, as they get more energy, more kinetic energy, they're gonna start moving around each other. And then we're going to have a liquid. And where water molecules are moving past each other and tumbling over one another, we have more kinetic energy, more movement, and we're in the liquid state. Here are units of energy that we'll discuss, or that we'll use to communicate how much energy something has. Now, the one you're probably used to is the calorie. This is what we read at the back of a snack packaging to find out how much energy it has. And that's really how much energy we'll get from it. And a calorie is really defined as the amount of energy it's going to take to raise the temperature of 1 gram of water 1 degree Celsius. So 1 gram of water increases from, let's say, 24 to 25 degrees Celsius. Now, the calories that you read at the back of a snack package is actually what we think of as a nutritional calorie. And if you look, that's usually a capital C. And really, a nutritional calorie is equal to 1,000 actual calories, or 1 kilocalorie. And we just apparently divide everything by 1,000, so that way you feel less intimidated about eating something. If it says 400 calories, you'd be like, yeah, yum, 400 calories. I need some energy. If it said 400,000, there might be some sort of struggle there, at least from an advertising perspective. And so we have, we need to keep in mind that 1,000 calories will be 1 kilocalorie, will be 1 nutritional calorie. And I like to always write out nutritional calorie rather than rely on a capital C versus a lowercase c, because I think that's a really confusing way to write 2 different units that are on different scales, because lowercase and uppercase c's can look really similar. And so for nutritional calories, I'll usually write it as 1 nutritional calorie to highlight that what we're really talking about here is 1 kilocalorie. Now, the unit of energy that we use more frequently in chemistry is the joule. And a joule is a Newton meter squared, but we can relate them through an equality or a conversion factor to calories. So 1 calorie will be equal to 4.184 joules. And these both can be treated just like with the metric system, using prefixes to increase the magnitude. Sorry. So we can have kilojoules and kilocalories. We can have microjoules and microcalories. So these are the conversions to get comfortable with and that we can now use to convert in the same way we've been using dimensional analysis throughout the quarter. Here's just a little bit of a calibrating tool to get an idea of how much energy things take. So if you're going to sleep, this is all going to be in joules, okay? So if you are going to be asleep, you're not going to use as much energy as being awake. You're going to use 10 to the power of 5 joules of energy to keep your body functioning for an hour of rest. Now, the energy that you would get from like a gallon of gasoline for your car, which will move you, 15 to 30 to 70 miles, depending on what kind of car you have, it's going to be 10 to the 8th joules. So significantly more. We use about 10 to the power of 11 joules per year in the United States for our personal energy consumption. And if we think about the United States, that consumption then is 10 to the 20th power. And on the upper end, 10 to the 26th, that is the amount of energy that's radiated by the sun in 1 second, which is impressive, an impressive amount of energy, but it's a giant ball of fire. So this kind of gives you a perspective, and you'll notice that we are going to be working with large numbers when we are doing energy calculations or discussing the amount of energy that something has. Let's look at an example. So a gummy bear, if you look at the back of packaging, is 9 calories. These are nutritional calories. So let's figure out how much energy is stored in a gummy bear in units of joules. And so right here, I've identified I have a starting point, and I've been asked about joules. So this is really my goal for this calculation. So I'm going to start with my 9 calories as my starting point, and I'm going to try to convert into units that are going to be joules. So my 9 calories that are nutritional calories are really 9 kilocalories. So I'm going to convert into normal calories by doing a metric conversion where 1 kcal equals 1,000 calories. So now I have 9,000 calories. Now I'm going to use my conversion between calories and joules, that 1 calorie equals 4.184 joules. And I'm setting this up so my calories will cancel. So for my conversion factor, calories is on the denominator and 4.184 joules is on the numerator. When I calculate this, I get this big number, about 37,660 joules. If I wanted to convert this into kilojoules, I would multiply this by 1 kilojoule, divide by 1,000 joules. I'll move this decimal place over 3 and get 37.66 kilojoules.